What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 11, Practice Test. Let's do it. Question 1 is the ordered pair of solution. So the way we're going to do this for the system is, this is a solution if I can plug and chug and get true equations for both. So I'm going to first check the first one, plug the x in there, plug the y in there. So I get negative 3 times negative 5 is 15 minus positive 3. Does that equal 12? Yes, it does. 12 equals 12. That verifies. Now I'm going to plug it in here. Plug in negative 3 for x. Plug in positive 3 for y. Okay, so 4 times 3, that's 12. Negative 3 plus 12, that indeed does equal 9, which means that this is a solution to the system. So we'll say yes, boom, done. So for this question, we're solving by either elimination or substitution. I'm going to choose to solve this with elimination. I generally like that method better. And I can see that if I match up the x's, okay, as to be the same constants but opposite signs, I can quickly knock them out. So I can multiply the top by 4. 4 times negative 1/2 is negative 2x. 4 times negative 4 is negative 16y. And then 4 times 4 is 16. Now we're going to add these together. So 2x plus negative 2x, that goes away, right? So that zeroes out. Then 16y plus negative 16 out. We didn't anticipate that, but that also zeroes out. So now we have 0 on the left-hand side. Then we get 2 plus 16, which is 18. So we get a funny equation because 0 definitely actually does not equal 18. So when we get something like this that is absurd, that doesn't make sense, we know that this is a no solution situation, meaning the lines are parallel, they never intersect. That's how you do it. Done. So for this triple system, I'm going to solve with a little bit of substitution. The way I like to start these is I group these two together and these two together, and then I'm going to choose a single variable to target and to eliminate. So I'm looking at these, and I think it's going to be pretty easy to get rid of the x's. So what I'm going to do for when I pair the first two together, I'm going to write the first one as is. And then since I want to get rid of the x's, I'm going to multiply this one by negative 4. Okay, so multiply the second one by negative 4. We get negative 4x plus 28y minus 20z is equal to negative 4 times negative 1/4 is positive 1. Okay, and for the bottom two, as I group these together, again, I'm going to eliminate the x. So since that's positive 3x, I'm going to multiply the second one by negative 3. So that becomes negative 3x plus 21y minus 15z equals positive 3/4, and then we leave that one as is. Now using elimination, I'm just going to add these together, or it's called addition sometimes. These are going to go away. That's what we want. Negative 6 plus 28 is 22y. Negative 2 plus negative 20 is negative 22z. And then 1/10 plus 1 is 11/10. Over here, as we add these together, these go away. 21 plus 6 is 27y. Negative 15 minus 9 is negative 24z. And then we got 3/4 plus 6/5. Let's get a common denominator. So that's 15/20 plus 24/20. That's going to be 39/20 equals 39/20. Okay, now we got two equations, two variables. We're good to go. Let's put them right underneath each other. And the other thing is, if we're going to continue to use elimination, I'm going to simplify these a bit. So the top one, I'm going to divide everything by 11. So then I got 2y minus 2z is equal to, that divided by 11 is 1/10. And then over here, let's divide everything by 3, right? We've got 9y minus 8z is equal to 39 divided by 3 is 13/20. Okay, much easier. Now to use elimination for these two, if I multiply this one by negative 4, I can knock out the z's. So I'll get negative 8y plus 8z is equal to negative 4/10. And negative 4/10, by the way, is negative 8/20. So I'm going to go ahead and write it that way so these have common denominators. Okay, let's add these together. Goodbye z's. 9y minus 8y is 1y. And then negative 8 plus 13 is 5/20. And that is going to reduce to 1/4, or 1/4. Now that we've got y, we can solve for z using maybe this equation. Okay, so let's say we've got 2 times 1/4 is 1/2 minus 2z equals 1/10. Now I'll minus 1/2 from both sides, right? Minus and minus, and that goes away. Then we got negative 2z equals 1/10, and then 1/2 is 5/10, right? So 1/10 minus 5/10 is negative 4/10. Okay, and then last but not least, divide by negative 2 means multiply by negative 1/2. and z would equal 4 over 20, right? The negatives cancel out, 4 over 20, which reduces to 1/5. So z is 1/5. Now I want to solve for x, so I'll plug these values into any of these three equations. Let's just do the top one just for fun. Okay, so we got 4x minus 6 times y, which is 6 times 1/4, which is 3/2. And then minus 2 times z, z is 1/5, so that's minus 2/5 is equal to 1/10, okay? Let's consolidate these a little bit. So we'll get a common denominator of 10, so that would be 4/10. Here, let's make a little room. Negative 4/10, that would be negative 15/10, and those will combine to be negative 19/10. So we got 4x minus 19 over 10 equals 1 over 10. Now we're going to add 19 over 10 to that side. This is going to be 20 over 10 or 2. So 4x equals 2, which means x equals 1/2. All right. So we got it all scratched together. Now let's write it out in a nice coordinate format. So we got x is 1/2, y is 1/4, and z is 1/5. And that's how you do it. Done. So for this one, again, I'm going to kind of group into those two and these two. And the variable I'd like to eliminate is y. Again, it's arbitrary. I could do whatever I want, but I just see a 1y in the middle in the equation that I'm using twice. So that's going to be easy to manipulate. So if I got the first equation as is like so, to knock out those y's, I'm going to multiply this one by 4. Then I get 8x plus 4y plus 8z equals 0. And then when I group the bottom two, I got a negative 6y, so I'm going to have to multiply it by 6 this time. So I'll get 12x plus 6y plus 12z is equal to 0. And then this one down here stays as is. So let's combine these together, and we get 13x, right? 5 plus 8. The y's cancel out. Boom, and then negative 3 plus 8 is 5z is equal to 0. Over here, the y's cancel out. We get 13x plus 5z is equal to 0. All right, great. Now we have two equations, but look at this. These are the exact same equations, okay? So 13x plus 5z equals 0. That doesn't do much for us, right? If we negate, we get 0 equals 0. All right. This means we have an infinite solution situation, and we can put everything in terms of x. I can start with this nice equivalency, right? I know that 13x plus 5z equals 0, which means 13x equals negative 5z, right? Subtract 5z from both sides. And then if I divide both sides by 13, I get x equals negative 5 over 13. And then if I divide both sides by negative 5, like so, I get z is equal to negative 13/5 times x. So now I know what z is relative to x. Now I just need to get an equivalency for y. And I can do that by plugging this in for z in any of those equations, but I'll just choose the top one and then isolating y. So we got 5x minus 4y, and then negative 3 times negative 13 over 5 is positive 39 over 5x is equal to 0. So I can combine like terms, right? Add these together. 5 is really 25 over 5. So 25 plus 39 is 64. So we got 64 over 5x. And I'm going to simultaneously, since I got it equal to 0, I'm going to add 4y to the other side and say that's 4y. And again, let's isolate y, so we need to divide by 4. So when I divide by 4, I do 64 divided by 4, which is 16. So I got 16/5 x is equal to y. So now if I put this all into coordinate format, I got x is x, y is 16 over 5 times x, and z is negative 13 over 5 times x. And that is how you do it. Done. So for this one, I'm going to actually do a little bit of elimination, although a lot of times substitution is a great go-to for these nonlinears. But look how nice it's set up, right? I can just add these together. But you know what I'm going to do is I'm going to actually negate the bottom equation. So everything's been multiplied by negative 1. Then these are going to cancel out. We get 3x squared equals 24. Okay, look at this. Now I'm going to divide both sides by 3. X squared equals 8. Last but not least, we're going to take the square root of both sides, and I get x equals, in simplest radical form, square root of 8 is 2 rad 2. But don't forget, this is a plus or minus. So it looks like we got two potential intersection points at positive 2 rad 2 and negative 2 rad 2 for x, okay? So let's write that out. We got 2 rad 2 and negative 2 red 2. There might be more solutions, but let's just roll with this for now. Okay, so now to solve for y, I can plug these guys in, right? So 2 rad 2 in for x squared, so that'd be y squared plus 2 rad 2 squared equals 25. Okay, 2 rad 2 squared we already know is 8. So this becomes y squared plus 8 equals 25. Subtract 8 from both sides. Y squared equals 17. And we take the square root. So that means y is equal to plus or minus square root of 17, right? But that plus or minus means that we got two solutions here, positive and negative rad 17. So that means with 2 rad 2, we've got positive rad 17, but then we have a second one, 2 rad 2 negative rad 17, okay? So we end up with two solutions there. So maybe we're going to have more than two, right? Because we should have at least 3 at this point. Now I need to plug this guy in to either equation, but I'm going to choose the top just for the heck of it. And the thing is, we're squaring it. So this is going to turn back into 8. This is going to be a repeat of last time. So guess what? This is again going to yield two more solutions. Positive rad 17 and negative rad 17. So we end up with 4 solutions. And it's 4 intersection points. That's how you do it. Done. So for this question, we're meant to graph this system of inequalities, and it's important to kind of recognize these standard forms. Like, what are these? Well, this one on top is a circle, and in particular, if you remember standard form for a circle, it's centered at 0, 0, and it has a radius of the square root of 4, which is 2. So we would have a point here, 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 and here. Now, I'm going to draw on that circle. And because it says greater than, it's an inequality, we're going to leave it dotted. That's going to imply that the actual values on the circle itself are not part of the solution set. Okay, and then we got this. Y is less than x squared plus 1. So what is x squared plus 1? That's a parabola, right? And it's a y-intercept of 1. That's also the vertex, 0, 1. And then it's going up, right? And now I'm just going to kind of sketch it in. We're going to go do like this. Again, it's a dotted line because it's less than, not less than or equal to, or greater than or equal to. And now we get to the shading part, right? So it's where it's greater than 4 is what it says. And what that means for the circle is we're shading everything outside the circle. If it was less than, it'd be inside. But we're gonna come back to that. And then but it's a system. So it's both greater than the circle, but then less than the parabola. So less than the parabola means everything below the parabola. So the combination of these two sections would be all of this. So there's my shading. It's not the best, but that gives you the idea. That's how you do it. Done. So for this one, we're doing a little partial fraction decomposition with a repeated linear factor. So the way we're going to do this is we're going to first set it up as is. Boom, 3x plus 1 squared. And this is equal to first a over just that linear factor, 3x plus 1. And then we have plus b over that entire denominator, 3x plus 1 squared. Okay, now we're going to multiply by that denominator, 3x plus 1 squared on both sides. Over here, it's just going to cancel out, and we've got 13x plus 2. And then when we multiply against this guy, that's going to cancel out with one of those. So we're left with a times 3x plus 1, like so. And then we multiply against here, these are going to cancel out completely, right? So we're just left with b. All right, now we can start to solve for a and b. And, you know, the first thing I can do is actually, I can do a little clever substitution, right? If I plug in negative 1/3 for x, what's going to happen is I'm going to have negative 1 plus 1, which is 0. And I'm going to be just left with b. And then b would equal negative 13/3 plus 2. And again, 2 can be rewritten as 6/3, which means b equals negative 7/3. Okay, now we can figure out what a is by plugging in, and we can come back to this equation. And I'll simplify it a little bit. 13x plus 2 equals 3x times a plus a, right, if we distribute the a. And then the b is negative 7/3. So we'll just plug that in there. Okay. And now what we can see is we know that these terms must match up, right? Because they're the only terms with an x in there. We could also figure out that 2 matches up with these two combined together, but this is easier. So that means 3a is equal to 13, which means a is equal to 13 over 3. All right, now we come back to this original setup and we replace those with these nice coefficients. So we're going to have 13 over 3. This is I'm plugging in for a, and then times 3x plus 1. And then we have minus, I'm going to say minus because that's negative. And then we have 7/3. So I put the 7 on top, 3 on the bottom with the 3x plus 1 squared. Now, this is a slightly different answer than the back of the book, but this is correct. This is indeed the correct way to decompose this fraction. However, the one in the back of the book is also an appropriate decomposition. You can see it still should be equivalent. So, but anyways, this is, I believe, the right way to do it. So that's how you do it. Done. So for this one, this is a nice scalar multiplication and then addition. And by the way, we wouldn't even be able to do the addition if the matrices did not have the same dimensions, but they do, so we're good to go. So let's do a step by step. So first we're going to do that scalar multiplication, literally multiplying everything by 5. So that becomes 20, 45, -10, and 15. And then for this one, we multiply everything by 1/2. So that's -3, that becomes 6. That becomes 2, right? And that becomes -4. And then we add the positions in the same, or add the numbers in the same position to each other, right? So it's going to be 20 plus -3 is 17, 45 plus 6 is 51, -10 plus 2 is -8, and 15 plus -4 is 11. And that is how you do it. Done. So for this one, we're trying to find the inverse of this matrix. So let's give the first step here. So first, what we're going to do is we're going to swap these two. So we got 1/5, and then that 1/2 goes down here. And then these two we're just going to negate. We're going to say that's -1/4 and -1/3. And then what I'm going to do is I'm going to multiply this by 1 over a times d, which is the product of those two, which is 1/10, minus these two multiplied, which is going to be 1/12. Okay. So now, what is 1/10 minus 1/12? Well, let's get some nice common denominators. They can both go into 60. So that's 6 over 60 minus 5 over 60, which is going to be 1/60th. And 1 over 1/60th is going to be 60. Okay. So now, as we multiply in with our nice scalar multiplication, it's 60 times each of these. So 60 times 1/5 is 12, times -1/3 is -20, times -1/4 is -15, and times 1/2 is 30. And that is how you do it. Done. So to find the determinant of this, first I'm going to write it out like so, and then I'm going to repeat column 1 and column 2 right here. Once we get to this position, we got a really nice setup. What we can do is we can take that product, those three multiplied, plus that product, and then minus, coming back the other way, that product, and that product. So let me show you what I'm talking about. 1/2 times 0 is 0, plus -1/2 times 1/2 times 0 is also 0, plus 0 times -1/2 times 1/2 is also 0. Okay, that's nice and easy. And then come back the other way. -1/2 times -1/2 times 0 is 0, but we're minusing those values in red. 1/2 times 1/2 times 1/2 is 1/8. Again, we're minusing that. And then triple zeros, that's obviously 0. So the only non-zero number we have is -1/8, which means our final answer is -1/8 for the determinant. Boom, done. So for this one, we're meant to rewrite this as an augmented matrix. So the way you kind of do that is we set it up like this with this little line here. And all these coefficients of x, y, and z just pop in on the left side. So we got 14, -2, and 13. So you think like this is like my x column, y, and z. And the same is going to apply for these equations down here. Again, -2 goes here for the x. And then we have 3 for the y, -6 for the z. Same down here, 1, -5, and 12. And then we put in those constants over here. So we got 140 with the first, -1 with the second, 11 with the third. That is how you do it. Done. Here we're going to do a little Gaussian elimination to solve this. So let me show you how we set it up. So first we do a nice little matrix, and we got the coefficients 1, -6, 2, -12, and we got a 4 and a 0. And the idea is to get this into 1, 1, 0, 0. Once we have that, we have our solutions. So I already got a 1 here. That's beautiful. I need to zero this out. So I'm going to multiply row 1 by -2 and add it to row 2 to get a new row 2. So we got -2 plus 2 is 0. Then we got +12 plus -12. Oh, we got another 0. Okay. And by the way, when we have all zeros, it's either going to be a no solution or an infinite solution situation. Then we got -2 times 4 is -8 plus 0 is -8. Interesting. So I have 0 plus 0 equals -8. Essentially, that's what that represents. That's nonsensical. So when you have a 0 and then a non-zero over here, this is a no solutions situation. So we'll say no solutions, boom, done. So for this one, we're going to use the inverse of this matrix to solve. So let me show you how we're going to start to set this up, right? First, we've got our matrix of these coefficients. We got 4, -5, -1, and 2. And remember those solutions on the other side. We're going to keep them here for now, and we're going to use them later. So -50 and 80. So to find the inverse, the first step is I'm going to swap these two. So we got a 2 up here, a 4 down here. And then these two are going to stay as is, but we're going to negate them as 1 and 5. And then I'm going to multiply by 1 over a times d, 4 times 2, which is 8, minus -1 times -5, which is 5. All right, so that's going to be 1/3, and we're going to distribute it into everything. So we got 1/3 times 2 is 2/3, times 5 is 5/3, times 1 is 1/3, and then times 4 is 4/3. Great. Now that's my inverse matrix. And then what we're going to do is we're going to multiply it against that one up there. We got -50 and 80. Okay. And what we're going to get is we're going to get a similar matrix like this in those same dimensions, but I'm going to expand it out a little bit so we have a little bit of room to write in what we got to do. So first we're going to multiply this matrix. We go this times this plus that times that. So 2/3 times -50 is -100 thirds. And then 5/3 times 80 is 400 thirds. And then we're going to do the multiplication on the bottom, this times this plus this times this. So that's -50 over 3 plus 320 over 3. Okay, let's simplify this a little bit now. So -100 plus 400 is 300. 300 divided by 3 is 100, and that's my x value on top. My y value is down here. -50 plus 320 is 270 divided by 3 is 90. So there's my solution, and you can plug in just real quick just to verify. Plug it into both equations. 400 minus 450 is -50. -100 plus 180 is indeed 80. So there's my final solution. Done. So for this question, we're using Kramer's rule, and the way we use Kramer's rule is we calculate the determinant of the original matrix, which is 200, -300, 400, and 715. So that's going to be D. And then we're also going to calculate dx and dy, and I'm going to show you how to do that in this problem. So now to get the determinant, we multiply there 200 times 715 minus 400 times -300. And that's going to give us 263,000 for the determinant. Now we need to calculate dx. The way we do that is we take these constants and we replace them with the x column. So we're going to rewrite this with 2 and 4 over here. The y's stay as is. And then again, to get the determinant, we multiply those two together. That's 1430 minus that product, which is minus -1200. So we're going to add those together, and that's going to be 2630, and that is dx. Last but not least, we got dy. So for dy, we're leaving the x's alone, 200 and 400, and we're replacing the y column with 2 and 4. Okay, to get the determinant, multiply. That's 800 minus that product, which is again 800. So check it out. We get 0. So dy is 0. Now to get x and y. To get x, we take dx divided by d, and that comes out to 1 over 100 when you simplify it. And then to get y, we do dy divided by d. 0 divided by anything is 0. So there's our solution. Done. A factory producing cell phones has the following cost and revenue functions. Boom and boom. What is the range of cell phones they should produce each day so that there is profit? So what we're trying to do really here is just figure out the intersection points, okay? And then once we figure out the intersection points when cost is equal to revenue, we got to look at the zone where the revenue is above the cost. So what I'm going to do is I'm going to set these two equations equal to each other first. Okay, and as we simplify, we can subtract these from both sides. They go away. And then I'm going to subtract 75x from both sides, and we get 2688 equals 85x, all right? Then I'm going to divide both sides by 85, and we get 31.6. So that's just rounded, right? But that's interesting. We only have one intersection point. So I was thinking there'd be a zone, but it looks like there's a single point where one crosses over the other. Now you can see, okay, and this is just from a logical perspective, you can see this revenue function is probably going to be growing faster than the cost because while there's this big constant here, that doesn't really do much as x increases, but this is bigger than this, right? And the x squareds are essentially the same. So my feeling is that it's when x gets bigger than this, okay, that's when this is going to take over. That's when this is going to be bigger. So we're going to say 32 or more, but we're going to verify that right now in Desmos. And you can see here that the red function is the revenue, and it does indeed start beating the x value at this point. And that's what we calculated, right? 31.6. So as we get above, and again, I'm choosing a whole number, right? I'm not saying 31.6 because we're making whole whatever it is, right? So 32 or more, and that's the point. And after that, the red function is always going to be above the blue function. Blue is again cost. So 32 or more is the final answer. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.